topic is diagonalization of matrix. Diagonalize. Missed out on spelling. Digital pen is giving me. So I'm just going to take an example, and using that example, we are going to see the answers. So I will just take up a 2 by 2 matrix. Okay, a 2 by 2 matrix. If we take this 2, 6, 0, minus 1. I'll just show you the steps, and based on these steps, you can definitely do it. Okay. And for this, the question is you have to just diagonalize this matrix. So I told you diagonalization means that you will have an element here, you have an element here, there will be 0 here, there will be 0 here. So that's what is diagonalization is all about. And you know, there are matrix operation based on which you can actually do diagonalization. There is nothing wrong in it. You can always do it. But then, you know, this is actually an easier method. Where we actually use the eigenvalue and eigenfunction. That's actually been the theme of the first unit rather. We've been doing this again and again. Okay, so maybe I can just write it down as 2 minus lambda. You can do it on your own and then do it. It's important that you are having that speed of solving the problem at the same time accuracy. So speed and accuracy both are very important. Okay, so since I'm teaching it in the class, so I don't need to do that fast. I really don't prefer going that fast even. I'll just take up 2 minus lambda. Then there is a minus, so I can just take it out, right? 1 plus lambda is equal to 0. So there is a minus, if this gets cancelled, because in the right hand side it's 0, right? So in that way, we can say that we have got two eigenvalues. One is 1, okay, and the other one is minus. One is minus 1 and one is minus 1, 2. So in case you see if there is any kind of mistake and all, please stop me in between. Okay, maybe message or just interrupt. So now we have got lambda is equal to minus 1, and in that way what we can do is we can actually find out the eigenvector, right? Let's just do it. The more we practice, it's better. Same goes for me also. Okay. So this is x1, this is x2, then we have got this as x1 and x2. Although I've been using this notation, x, this one, basically showing you a column matrix, right? And this is actually for a row matrix. Use that also, but then let me just keep these things simple here, okay? And then we know this is 2 times of x1 plus 6 times of x2 is equal to 0. Okay. Right. And 2 times of. So in that way, if we just solve it, write down that x1 is equal to, so am I doing it correctly? Yeah, seems okay. Oh, sorry. There is a minus 1 right there. That's not correct. We're doing it for minus 1, so it is minus 1 here. And then we have got it here as x1 and x2. Right. So just write this here. It's minus of x1. Right. Then just take it on one side, and then 3x1 is equal to 6x2. So x1 would be minus of 2 times of x2. Right. And do the other one also. You should get a similar result. Okay, I'm not doing it. So for lambda is equal to minus 1, we have got the eigenvector. I'll just represent it as v1, v for vector. Okay. is equal to minus 2 and 1, right? This one I think you remember. I can assume one value. Okay, let's say let x2 is equal to x2 is equal to 1. So x1 is equal to minus 2, right? So that means we'll return it as minus 2 and 1, right? And let me just find it out for lambda 2. I've not done the calculation, that's why I'm doing it, okay? So that's why I'm telling you this. Check it once. 260 minus 1. And do tell me if there is something wrong there. x1, x2 is equal to, this is for 2 and this is x1, x2, okay? And then this would imply this is 2 times of x1 plus 6 times of x2 is equal to 2 times of x1, right? So if you just do it, we know that
Sir,
6, yeah,
so for lambda equal to minus 1, should we
uh-huh.
take a normalized uh, form of
Yeah,
that?
yeah, we can take normalized, but we're in diagonalization here, okay? So I'm not really using the normalization thing. Let's just complete this, and you'll see that you don't really need the normalization part factor. You directly diagonalize it, okay? So our aim is actually to get rid of this part. Okay? To just make this 0, 0 and then diagonalize it, okay? That's what we're
Okay.
doing, okay? Let's just try. Let's finish this. X2. So here we can say that x2 is equal to 0 and x1 we can take any arbitrary constant. X1 is equal to 1. We've done it. Okay. So for x1 is equal to 1, x2 is equal to 0. If you just be sure that delta 2 equal to 2, take vector 2 to be 1 and 0. Okay. So we have this, okay. So yesterday I told you, I think we did not do anything, but we have to just do it, okay. We have to find out something which is called the P matrix, okay. That's the first thing that we do in diagonalization. Okay, we're going to calculate the P matrix now. So it is minus 2, 1, 1 and 0. So these two we have to remember for the next slide. So now what we are going to do is form P matrix. I'll finally give you the steps for P matrix. This is actually the easiest way to diagonalize. Okay, even if you don't know any kind of matrix operation, this probably should be easy to find out. So we have got P is equal to, we'll just write down the vectors here, vector 1, then vector 2. Okay, so this is minus 2, just cross check it, 1, 1, 0. Okay, I'm also doing it with you. I need to do it. Okay, this is P. We also need to find out P inverse. I'll tell you where we use it, how we use it. P inverse. Okay, so P inverse is adjoint of A divided by determinant of A. Right? So yeah. So A E. So let's just find out what is the determinant of P. So this is our P. So this is minus 2 into 0 is 0, 0 minus 1. So this determinant is minus 1. How do we know? And for adjoint of A, let's find out what is the cofactor. So maybe I just write it down as EC and find out the cofactor here. The cofactor would be, if I take this, this is 0, right? And this particular term is, here we have got, cancel this out, this is 1. This is first row, first column, so it will be 1, right? Sorry, this is, yeah. This is minus 2, 1, 1, 0, okay. So this is first row, second column, so it is minus there. So it will be minus 1, okay. Please don't mix up, okay. Please check and I'm going, this is 1, so I can out, there's a minus here, so this is minus 1. So that means this will be minus 1, and then I will take this term, cancel this out, this is again positive, so this is a minus 2 there, so I'll put it as minus 2. So that's the cofactor term, it's correct. End of the day, we'll see that we actually are able to find it and check it also. Then we'll take the transpose of this cofactor. So this is 0 minus 1, and then this will be minus 1 minus 2. Right? So that's your adjoint, right? Adjoint. We have this now. Next is to find out P inverse, right? So P inverse is, this is minus 1, and this is the adjoint. I'll just take it directly rather. 0 divided by minus 1 is 0, minus 1 divided by minus 1 is 1, minus 1 divided by minus 1 is 1, minus 2 divided by 1 is... Someone's mic is on, can you just mute that? 0, 1, 1, 2. Okay, so we have got the P inverse now. Now the next thing is actually to check what you can do, whether we have calculated it correctly or not. This is what I prefer you doing. Don't do it in exam, you actually just do it in graph, so that you are sure at every step that you are getting the correct answer. P inverse, right? So you know you have got P matrix and P inverse. Both of them should give you a diagonal matrix with the component is 1, right? Unit matrix. You've got minus 2, 1, and then 1, 0. Okay, this is P, and P inverse we just calculated to be 0, 1, 1, 2. Okay, and if we do this, this is C2 into 0, this is there, no 1 is 1, so this is 1, fine. This minus 2 into 1 is minus 2, 1 into 2 is 2, minus 2 plus 2 is 0, fine. This into this, 0, 0, so this is 0.
Yes, sir.
And then
Identity
this is correct, right? So it is a diagonal matrix. And this is correct, right? So, you know, whenever you do it, maybe a 2 by 2 or a 3 by 3 matrix, what I like all of you to tell is just have a practice of checking. Okay, I think, you know, if you just check it once, then you become confident. Okay, because even I have not done it, so I'm doing it now. I'm checking it once so that I'm sure that okay, whatever steps we are doing is correct. But don't include it. You really don't need to include the check part. Okay, it's just for our satisfaction that in between we're doing it correct. That's the beauty of doing mathematical physics. Okay, so if we just want to find out the diagonalized matrix now, okay, diagonalized. Okay, we present it as D, let's say. Okay, and if we just diagonalize it, we have to just write it down in the form P inverse A of T. If we do this operation, this matrix operation, we should be able to get the diagonal matrix. Okay, let's see. So D is equal to 0, 1, 1, 2. That's P inverse. Then we will write down our A. Please keep checking on writing the correct thing. 0, minus 1. And then I will write down my P inverse. That's minus 2, 1, 1, 0. Right. So if you just do maybe just keep the 0, 1, 1, 2, 1. And then just do the second part. Second part would be 2 into minus 2 is minus 4, and 6 into 1 is 6, minus 4 plus 6 is 2. Then 2 into 1 is 2, this is 0, so this is 2. And 0 into minus 2 is 0, this is minus 1, so this is minus 1. And then this is again no 0, 0, so this is 0. That's multiplication of this and this. Right? And then you can multiply 0 into 2 is 0, 1 into 1 minus 1 is minus 1. Just put minus 1 there. Then this into this 0, 0, so this is 0. So this is this into this 1 into 2 is 2, 2 into minus 1 is minus 2, plus 2 minus 2 is 0. And then this is 1 into 2 is 2, and then 2 into 0 is 0, so this is 2. So yes, look at it. This is the diagonal, this is the diagonal part. Diagonalize the matrix. You do it usually using matrix solution. It's done. It's standard procedure. Issue. Then this is also the one that we can actually use. So this is the technique that we are going to see. Check. Okay. So check it. So we can actually do it using even 3 by 3 matrix also. So for 3 by 3 matrix, maybe we can practice once. Okay. So steps to diagonalize. Okay. Number 1, take the matrix, find out the eigenvectors. Maybe it will be 1, 2, and so eigenmatrix. Yeah, eigenvector. Sorry, that's the first step. The second step, we have to form the P matrix. Okay, so P matrix, you have to just write it down in this way. See, it's a square matrix. What you're going to get? Form the P matrix. Second step. Third step, find P inverse. Fourth step, find the diagonalization. Diagonalized matrix. That's the final answer. P inverse A. So these are the 4 steps that we have to do and diagonalize a matrix. Okay. Let me just give you one matrix on random and you try doing it. Okay. I don't know. I'm totally. I don't have any reference for this. I'm just doing it now. And maybe I'll give a matrix like this: A 0 2 1 minus 1 0. I should not take 0 at the time. Maybe create addition of problems. Minus 1 1 2 2. Some small values and 1 1 minus 1. So this one you can try. And let's see if you get an answer. Maybe homework over there. Okay. So done 2 by 2. You have to practice a bit on 3 by 3. Okay. And then it will always be better. Okay. Okay. Let's just go to the next topic. Okay. And the next topic is Caley-Hamilton theorem. Okay. So the next topic is Caley-Hamilton. So when you do these mathematical physics and all, okay, vectors and all, you know that you may have a lot of theorems, and if you just write down the general form and try to understand it, it takes a bit of time. So whenever we take up an example, it becomes more easy. Okay, so here also I'm going to do the same thing. I'm going to take up an example and the statement. Okay, you can just give it the statement here, and then once you do a problem, you'll know that okay, the statement is making a lot of sense. A square matrix, okay, considering a square matrix, satisfies own characteristic equations. Okay. So that's actually what is the Caley-Hamilton theorem is all about. Okay, it means that you basically have the eigenvectors. You can replace it by the the matrix itself, and that should actually be satisfying the left hand side and the right hand side. So in general, if I just write down an equation, it is A x, okay, the matrix into the eigenvector is equal to the eigenvalue into, okay, so this is the form that we have, okay, and it should satisfy this characteristic equation. So we have been using this characteristic equation. If you're still not comfortable with the term, please try recalling this. Okay, this is our characteristic equation. You have to remember certain things, very important. Okay, eventually we are going to land into units where we're just using the term and we are not explaining the terms. Okay, so in your book also you'll see a lot of books that directly use the term. Okay, so we have to just refer back to our previous knowledge to understand it better. Okay. Okay. So let's try doing this. Okay, let's try doing this problem. Uh, let's take an example. Simple, okay? It's not difficult. I'll take the same example because then I don't have to really worry about the eigenvalues. Okay, so 2, 6, 0, minus 1. Okay, and then we can actually form the characteristic. I think this was the same thing that I've taken before as well. 260 minus 1. Okay, so we have the eigenvalues as minus 1 and 2. We have also got the eigenvectors. Okay, so it satisfies the equation means in this way. What we do is the first step, we actually write down the characteristic equation. We write down a minus lambda I. We are not going to find out the values right now. This is going to write down the characteristic equation. So that means you can just simply write it down as 2 minus lambda, this is 6, this is 0, minus 1 minus lambda is equal to 0. Okay? If we just do it, we're going to get it as 2 minus lambda 1 plus lambda is equal to 0. And I'm just going to open the brackets here. There will be 2 plus 2 lambda, and then minus lambda square is equal to 0. So if we just make one more line here, lambda square minus 2 minus lambda is minus lambda, plus lambda. So I'll just write down lambda square plus lambda, okay, minus 2 is equal to 0.
Lambda square minus lambda minus 2 equal to 0.
Uh-huh.
Sir, lambda square minus lambda minus 2 equal to 0.
Lambda square, oh sorry, yeah. Minus. So that's the equation that we have to write down. Okay, lambda square minus lambda minus 2 is equal to 0. Okay, so if you just do it, okay, because we have just taken out the minus common and divided on both sides. I'm taking it common and done it on both sides. Okay, so this is the characteristic equation that we have here. This is the characteristic equation that we have here. Now what we do is we actually replace these eigenvectors, okay, by the matrix. So a square minus a minus 2 identity matrix, which is a 2 by 2 matrix, is equal to 0. So 0 is, that's the matrix form. So that is writing down there. Okay, so this should be satisfied, and if this is satisfied, we say that the Caley-Hamilton theorem is satisfied. Okay, so a square matrix satisfies its own characteristic equation. So see this. This is a square matrix, and this is the characteristic equation that we have, and this will actually satisfy. If we put a in place of lambda, it should actually satisfy the equation. That's actually the theorem. Okay, but if we do a sum, I think it becomes much more easy. It has got other applications, right? So I've not really done it. Let's check if it really satisfies. A square is 2, 6, 0, minus 1, and then again 2, 6, 0, minus 1, square equal 2 into 4, and then this is 0, 2, 4, right? And then this into this 2 into 6, 12, 12 minus 6, this will be 6. And then this is 0, 2, 0, 1, 0. So this is 0, this is 0, 6, 0. So it's 1 minus 1 is plus 1. Okay, so 1. So that's your a square. And then maybe you can just write it down. Okay? I'm doing it just for my own satisfaction. If I do it and I see that okay, I'm getting the result, I feel happy about it. Right? Nothing more satisfying than this. Minus of 2 times of 1, 0, 0, 1. Right? And this is 0, 0, 0 or not. Let's check this. 4 minus 2 is 2, 2 minus 2 is 0, so that's 0. This is 6, this is minus 6, 6 minus 6 is 0, then minus 2 into 0 is 0, that's 0. Then is 0 minus 0, that's 0, that's 0, 0 is 0, minus 0. 1 plus 1, right? Minus plus 1, 1 plus 1 is 2, and minus 2 into 1 is minus 2, minus 2 minus 2 is 0. So it satisfies. So maybe I'll give you a question and what is Caley Hamilton theorem, okay? And prove it using an example, maybe, or maybe I'll just give you a matrix and tell you to just do it, okay? Should not take much of a time. You know, these things you've done a number of times, but sometimes we miss out under what theorem. Okay? So that's important. But then there is one more advantage with the Caley Hamilton theorem. We can also find out the inverse, okay? Inverse, you know, we have to do this adjoint and all and then find out. But we can also find out inverse using Caley Hamilton theorem because we have got this characteristic equation and we can actually just do a bit of use of this. Okay, so what we do is we can multiply with inverse on both sides. A inverse of a square minus a minus of 2i is equal to, this is 0, 0, 0. This side if you multiply A inverse with the 0 matrix, you're still going to get the same. So what we have here is this A inverse into A square, so it will be just A. A inverse into A will give you the identity matrix I or matrix property minus 2 times I into A inverse will just give you A inverse. So it will be 2 times of A inverse is equal to the 0 matrix. So I think directly put 0 also, it doesn't matter. So let's see what happens here. This is 2 times of A inverse is equal to, this will go on that side, A minus I. A minus I over here. And then we'll just take up A inverse. We need to find out. This will be half times of A minus I. We're all practicing it together, okay? That's it. Should get your A inverse. So A inverse निकालते हैं फिर. So from this, if you want to calculate A inverse, you can just simply write it down as half, and then A is my favorite matrix, 2 by 2, 2, 6, 0 minus 1 minus I. It is 1, 0, 0, 1. Right. We'll just keep it in terms of half, I guess, and just write it as half of 2 minus 1 is 1, 6 minus 0 is 6, 0 minus 0 is 0, and then minus 1 minus 1 is minus 2. We'll just keep it like this. But this should be my A inverse, okay? Check. Let's do a bit of check. A inverse is equal to 2, 6, 0 minus 1, and then 1, 6, 0 minus 2, and then of course there's the half there. Okay, so this is 2 into 1, 2, half, this is 2, this is this into this, 2 into 6, 12, minus 12 is 0, this is 0, 0, 0, 0, sub 0, this is 0 into 6, minus 2 into minus 1 into minus 2 is 2. We get a identity matrix. This is the identity matrix. So that means my A inverse is correct. So you know what I prefer is whenever you find out A inverse, just cross check. Okay? It hardly takes time. I think it's more important to be correct. So it hardly takes time. You should be able to. Okay. Let's try one 3 by 3. Okay. 0, 4, 2, 1, 3, 1, minus 1, 2, minus 2. Okay, so I'll give you a matrix like this and show that it satisfies Cayley-Hamilton theory. Show that it satisfies. Lazy, so this I don't see it. Theorem, and hence find A inverse. Try doing this and tell me if it's really happening. It's just a random.